a golf ball placed in this small car, expelled by a spring. What can this possibly have to say about a new physics?
This is one of those little toys that physics professors invent in order to demonstrate to their classes the meaning of physical theories. This one has to do with a considerable change which took place in science in the 17th century concerning the role of force in the motion of heavy objects. You know, there's a strange thing here. It's conceivable that you and I, in our everyday thinking, are still relying on physics which was made obsolete 300 years ago.
Whenever the motion of physical objects is discussed by a group of scientists, it becomes apparent that the common sense point of view of the non-scientist is greatly at variance with the currently accepted principles of physics. On further analysis, the common sense point of view proves to be a kind of physics that was invented a long, long time ago. In fact, about 2,000 years ago by Aristotle. Aristotelian physics was based on the belief that the earth cannot move but must be fixed in space. Thus, the ideas of motion that men have if they don't study modern physics are built upon a premise contrary to the concept of an earth moving through space in its orbit around the sun and simultaneously whirling on its axis like a top. Now, Aristotle held that earthy matter is either heavy or light. Smoke, which is something like air, is light, but stones and sticks and living matter are heavy. Now, according to Aristotle, each object tends to seek a natural place, which means that light bodies move upward, like the flame and the smoke from my cigarette, and heavy bodies move downward. A rock, a stick, or this cigarette are heavy. They tend to fall down in a straight line, whereas smoke tends to rise straight upward. If I drop this cigarette, we can see that while it falls down, the smoke will continue to rise, both cigarette and smoke seeking their natural places. Now, consider another possibility. In my hand, I hold a rock. If I allow that rock to fall, it moves straight downward. Yet a rock doesn't always move straight downward. I can take this rock and throw it up into the air. I can even take a rock and throw it across the room. I can take a ball at the end of a string and whirl it about, thus making a heavy object follow a circular path rather than a straight downward motion. But in each of these three examples, we see a kind of movement which was described by Aristotle as a violent motion rather than the natural motion of the body. By this he meant that in order to make a ball move upward, to make a ball move across the room, an external force would have to be applied. The force was the cause of that body moving in a way contrary to its nature, contrary to motion straight downward. Now, in the circular motion, which I impart when I whirl a ball on the end of a string, the violent motion contrary to the nature of that ball is imparted by means of the string through the continuous agency of my hand, which exerts the force. Now, there's one final point to be made about the Aristotelian theory of the motion of earthly bodies. All motion of bodies that we observe on Earth occurs in some kind of medium, be it air or oil or water. In such a medium, the speed depends on the resistance, as everybody knows. A man who drops from an airplane will fall very, very slowly if he has a large parachute to slow him down, but without it, he'll fall very quickly. In one case, there is a resistance to slow him down. In the other case, there is not. Now let's consider bodies of a single shape, spheres, which presumably will have the same resistance in a given medium. Suppose I perform an experiment in which I take two objects and allow them to fall, one of them to fall in the cylinder of water, and the other through a column of air. Now these two objects, which I hold in my hand, are both spherical in shape. They're both about the same size. When I drop them, one is going to fall in water, one in air. I let them drop like this. The first one is struck in the air, and there the one moves down very slowly. It's easy to see that the one that falls in air struck the sand long before the one that fell in water. Hence, there certainly can be no quarrel with Aristotle's conclusion that the speed with which a body falls in its natural downward motion must always depend on the resistance of the medium. The speed being small in a highly resistant medium like water, and being very great in a less resistant medium like air. Now, let's ask next, what would happen if I were to take two objects similar in shape but of different weight and drop them in one in the same medium, water? Now, this ball is made of steel. It's very heavy. It therefore has a much greater tendency to reach its natural place downward than this ball, which is made of wood and which is lighter. Hence, according to the Aristotelian or common sense physics, we would expect that if I were to drop the wood and the steel ball together in the water, that the steel ball, because of its greater weight or greater tendency to reach its natural place downward, should cleave the resistant medium of water more efficiently than the wooden ball, and so should reach the bottom first. This too may be demonstrated. I drop the steel ball and the wooden ball together into the column of water. Let's see what happens. The steel ball went down very quickly, and now there is the wooden ball following much later. Now let's follow the Aristotelian argument one step further. If the resisting medium is air and not water, surely the same effect will follow. If I were to take a 10-pound ball in one hand and a 1-pound ball in the other and drop them simultaneously from a tower, would I not find that that heavy ball has a greater speed and strikes the ground first? Apparently, there's no disagreement between the conclusions of Aristotle and the conclusions of common sense. Now there's one more point that was made by Aristotle, and that is that the matter of the heavenly bodies is actually different in kind from the matter of the earthly bodies. The natural motion of heavenly bodies is circular. It has no beginning and it has no end. But terrestrial bodies, whether heavy like rock or light like smoke, will move naturally in a straight line downward or straight upward, but not the heavenly bodies. The planets, the sun, moon, and stars move naturally in great circles, as you can see here. Now, if we accept the Aristotelian principle, at once we understand why sun, moon, planets, and stars move in their eternal circles around the earth and don't move in straight lines. But consider now some of the effects that would arise if the earth were in motion. According to the heliocentric system, presented in antiquity by the astronomer Aristarchus, and again in 1543 by Copernicus, the earth has a double motion. It rotates on its axis once in every 24 hours, and it moves in a great orbit around the sun in the course of a single year, as can be shown in this small model. There the earth rotates about its axis while moving around the sun. Now the earth is a large sphere. It's actually about 24,000 miles in circumference, a fact which was known to the Greeks. Suppose the earth were to be rotating on its axis, then any point on the equator would be moving through those 24,000 miles in 24 hours or moving along with a speed of 1,000 miles an hour, about 1,500 feet in every second. Now, let's suppose that at this spot on the equator, a ball were to be dropped from a tower 150 feet in the air and fall until it reached the earth. The time it takes is just about 3 seconds. The ball falls straight down from the tower to the earth. But as that ball falls from the tower to the earth rotates. And therefore, if the earth is thought to be moving, while the ball falls, the earth rotates and the ball lands here. It doesn't land at the spot directly underneath that from which it was dropped, but at a spot almost 5,000 feet to the west, about a mile away. But surely, everybody knows that a ball dropped from a tower 150 feet high does not strike the earth to the west of the tower, but rather strikes right at the foot of the tower. So there's an obvious conclusion. The earth can't rotate about its axis, unless, of course, the physical concepts of Aristotle are wrong. Now next, consider the motion of the earth in its annual orbit around the sun. The distance from the earth to the sun is about 93 million miles, which means that the earth's annual motion takes place along a large circle which has a radius of about 90 million miles. The speed with which the earth must move in that orbit in the Copernican system is about 20 miles per second. Now, if the earth were rushing through space at a speed of 20 miles per second, 70,000 miles per hour, yes, I said 70,000, surely we would expect to have some sensation of that motion. Just think of a bird clutching on to the limb of a tree for dear life while the earth is rushing by, and knowing perhaps that if for a moment it let go, whooshed, the earth would rush by and the bird would be lost out in space and never be seen on earth again. And what of that experiment of dropping a stone from a tower? In terms of the earth's motion along its orbit, we would have to make the following conclusions. First, a weight is dropped from a tower 150 feet in the air. It takes that weight about 3 seconds to fall down and reach the ground. During those 3 seconds, the earth moves a distance of something of the order of 60 miles. Now surely, under those circumstances, a weight would never strike the earth, even anywhere near the place from which it was let go. And so once again, we have to conclude that the earth is not in motion, unless Aristotelian physics is wrong. In other words, it's perfectly clear that if we shift from the concept of a stationary earth to a moving earth, we have to jettison the whole concept of common sense physics. For the men of the 16th and 17th centuries to accept the Copernican system, they had to throw out all the old common sense physics because it was based on the postulate of the earth standing still. In the new system, with the earth and planets moving around the sun, there was required the birth of a new physics. Now, the major principle of the new system of physics, which we associate primarily with the names of Galileo and Newton, is called the principle of inertia. This principle holds that for all matter, whether terrestrial like a rock or a planet, there is a natural state. It may be a state of rest, of no motion whatsoever, or it may be a state of motion in a straight line at constant speed. Now, this principle says that if there is no force whatever acting on a body, that body will continue to remain at rest if it is at rest, or it will continue to move in straight line at a constant speed if it is in motion. Now, this principle is directly contrary to the basic principle of the older Aristotelian physics, because it held that the natural state of an earthly body like a rock and of the earth itself was rest, and that the natural state of heavenly bodies was motion uniformly in a circle. Now, at the time of Galileo, some thinkers had come to doubt the validity of Aristotelian principles. Let's take that earlier one, the one which I presented as if it were true and which seemed to be so reasonable. I said, if two bodies of the same shape but of very different weight are dropped in the same medium air, the one with the greater tendency to descend would have a much greater speed and would arrive at the Earth first. In 1586, a report of such an experiment made by the Dutch physicist, engineer, and mathematician Simon Stevin was published. What he did was to take two unequal weights, drop them from a height of 30 feet, to find that they struck the Earth practically simultaneously and not at different times as everybody believed. And this was true even though one of them weighed 10 times as much as the other. Now I can repeat this experiment. I can do it by using this small marble and this rather large golf ball. The golf ball is much heavier than this small marble, and so if I think in terms of the Aristotelian physics, the conclusion is that this heavy one should go down and strike this box of sand first. Now let's make the experiment. I take the two balls and I hold them at about the same height above the sand and let them go. You can see they strike the sand at about the same instant, even though their weights are very different. This experiment can be repeated again and again and again. And in every case we find that, save for very slight differences, the result is this. They reach the sand in about the same instant. The better the apparatus for letting them fall exactly at the same time, the better the result will be. Now, before we examine the validity of this principle of inertia, the basic principle of the new physics, let me point to some of its implications for the science of astronomy. If it's true that except for a force, a body will either stay in the same place or move along in a straight line at constant speed, then the motion of a planet around the sun, the Earth around the sun, as in the Copernican system, must be due to the action of a force. Let me go back again to that example of a ball whirling around on the end of a string. As I make the ball whirl, the reason it keeps moving in a circle and doesn't move in a straight line at constant speed is that a force is being exerted. The force being supplied through this string by the agency of my hand. Now let's suppose that the string were to break, or that while the ball were moving, I were to let it go. Like this. While the ball is moving, I let go, and the ball flies across the room. It actually left flying along a tangent. It started moving in a circular path and then went across along a line tangent to that circle. This is, in fact, the origin of that very familiar expression, flying off at a tangent. Now, in the older physics, the reason why the planets and the sun could continue to move around the Earth was that for celestial matter, the circular motion was a natural one. But in the new system of physics, the reason why the planets don't move in a straight line at constant speed, but follow a circular path around the sun, is that there must be a force emanating from the sun which maintains them in their circular orbits. The reason that the Earth continues to move in a circle around the sun is that the sun exerts a pulling force on the Earth which prevents it from flying off at a tangent. Now, when the ball whirls around on a string, we can actually see how the force is transmitted through the string. Newton argued that it must be the same kind of force which keeps the Earth moving in a circle around the sun, even though there is no string and even though we cannot see any possible cause of it. To the cause, he gave the name of the force of universal gravitation. But what about that original problem? The problem of a rock let fall on a moving Earth. Physics actually tells us that the experiment of dropping a rock from a tower isn't really any indication of whether the Earth moves or whether it's standing still. In the days of Galileo and Newton, the classical argument about where a falling object would land was always presented in terms of the example of a ship. Take a rock, carry it up to the mast of a ship, men said. Let the ship be in motion. Drop the rock, and where would it fall? Surely not at a point at the foot of the mast, directly underneath the point from which it was dropped, because, they said, the rock was falling straight down, but the ship was moving forward. But remember, this is the argument of common sense, even if it's the argument still believed by most people who haven't studied physics. But according to the new physics of Galileo and Newton, the forward motion of this rock is independent of its falling down. If a rock is dropped from the mast of a moving ship, it will continue to move forward at constant speed, just as the ship does. This is the result of that principle of inertia. One of Galileo's admirers took a ship out in the harbor, climbed up on the mast, dropped weights from it, and proved that Galileo was right. Now here's a picture of a torpedo being dropped from a moving airplane. The torpedo falls down, pulled by the gravitational force of the Earth's attraction. But in the forward direction, the torpedo's motion is constant. It moves along directly underneath the airplane so long as the airplane continues to move in a straight line at constant speed. Now today, we can make an experimental test right in the laboratory. This little car contains a spring mechanism which is arranged so that it can be tripped by means of a lever. There, you heard the sound as the spring was being released. In use, the car is loaded by pushing down on the spring until it catches. Then a baffle is placed on the top in order to help catch the ball and prevent it from bouncing out. Then the little golf ball is placed here. And now, if the car is placed on a track, here you see a picture of the car, picture of the track. There is a little lug there which will move the lever. When the lever is moved, the spring will be released and the golf ball will shoot up in the air. Here's a pole to enable you to push the car along the track. Now, as the car starts down the track, the lug will be engaged, the lever will be tripped, the spring will be released, and the ball will go upward. But where will it land? When the ball is shot upward in the air, will it go straight up in the air and come down again behind the cart? Or will it fall in such a way as to strike the cart just in the place from which it was shot out? In other words, as the car moves forward, will the ball fall straight down behind the advancing car, or will the ball continue to move forward and drop back in the cup? Well, most people today who haven't studied physics would probably say that the ball would go straight up and down while the car went ahead, that the ball would fall behind the car. This is the same as the example of the moving ship. This is the same as the problem of the Earth. To those who would say that the ball would not land in the car but be left behind, Aristotle would have agreed. And so would the men who were living at the time of Newton and Galileo. But the principles of the new physics say just the opposite. The principle of inertia tells us that this ball will continue to have a forward motion as it moves through the air, just as it did when it was attached to the car. That the ball continues to move forward with constant speed while it's in the air, just as when it was resting on the car. Now, watch this film of the whole motion. You see, The ball shoots up, moving forward at the same time, keeping up with a little car and landing in it. Let's see it again in slow motion. You see, even if the Earth is moving through space at an enormous speed of 20 miles per second, a ball or a rock thrown up in the air will continue to have the same forward motion that it had while it was on the Earth. It will therefore go up in the air and land directly in my hand. And the extraordinary thing is that it will do so whether the Earth is in motion or whether the Earth is at rest.
I don't suppose you expected this golf ball shot right into the air to land back into this little car. You can see why the new physics, that of Galileo and Newton, was better than that of Aristotle. It explains effects of this kind, new effects, as well as the old ones. And there is a moral to this story. What we call physics consists of all the most fundamental laws that we have been able to find about the material universe. If one were in a critical mood, one could complain that there are a great many things that these laws know nothing about, and also that they are rather poorly knit together. But at least they are solid as far as they go, they work, and then they are very basic. They apply to every aspect of the material universe. They apply to the stars, and also they apply to the simpler problems about electrons. So that when something really new and important is found in any part of physics, that has repercussion on all our ideas about the whole universe. Not only about our ideas, but about the things we are going to do in using these new physics. When we say that the Earth is going around the Sun and not vice versa, our best reason is a certain theorem formulated in the 17th century by Newton. Now, some 300 years later, we are building a new physics too. Very likely that will have very wide consequences. For instance, that mankind should be able pretty soon to tap inexhaustible sources of industrial power, maybe just only one of them.
This is National Educational Television.